Okay, so let me give you the attendance. So yesterday we made a small introduction to operating systems. And we came up to this point, history of the operating systems. We didn't say much actually yesterday. Let's go over the things that we talked about. Maybe you had some questions because you guys didn't attend the class in face class yesterday. So we said that we are going to look at this concept of operating systems. And although we hear this term operating system a lot, usually people are confused about it. And we are trying to understand what the operating systems are, and we are going to see the details of it. We said that there are two things that the operating systems do. Okay, first they hide the details of the complicated hardware, okay, from the end user, from the programmers. Okay, because hardware is complicated, we have very complicated CPUs and the memory systems and the input-output devices and etc. So in order to make my programmer life easier, I hide all those details. To open a file, all I do is just to call the open function of C, and that's it. I ought to make a system call to the operating system, and it opens the file. The file could be opened on a network drive or on a hard disk, on an SSD drive, on a floppy disk. I don't care. The technologies are so different, but I use it the same way. Okay, so that's the hiding of the details from you. That's one thing. The other one is this management of the resources. Okay, computer has lots of resources. Like CPU is a resource; it has to be managed very carefully. Memory is a resource. The file system is a resource. Input-output devices, etc. It has to be all managed. It has to be protected. I mean, as an end user, I can't do anything that I want. I should be restricted. There should be some constraints. There should be some controls and etc. So that's the second thing. That's the second thing what the operating system does. And while operating system are doing these two things, it has to be efficient. It has to be easy to use, and it has to be useful. Actually, I mean, like I said yesterday, nobody uses a computer to use an operating system. Okay, operating systems are not our end goals in a computer. Why I use this computer to make a presentation? Okay, that's why I'm using this computer. Why am I using this computer? I am using it to communicate with my friends and colleagues. Okay, those are the reasons why we are using computers. I am not using this computer just to able to use Android mobile system, right? I don't care what kind of operating system runs on it. I am after, as a user, I am after my final thing. So it has to be useful. It has to be efficient. So it has to do these two things in that way. That's what we talked about yesterday, and we talked about this abstraction layer between our hardware and our user programs. Okay, but I cautioned you yesterday saying that, I mean, this doesn't mean that none of our programs are using the hardware directly. Sometimes we use the hardware directly. Okay, it depends how much permission we get from the operating system. Well, obviously, I'm going to execute my assembly instructions directly on the hardware, as long as I am using those allowable instructions. But if I like to access somebody else's memory, or if I like to, let's say, change the page tables. Page table is a special part of the memory. We are going to talk about it. Then I am going to be denied access. Okay, so operating system is kind of regulates all those access stuff too. Okay, so we talked about these, and we talked about this kernel mode. That was important. Kernel mode. CPU has two modes. Very broad, in very broad terms. Sometimes it has more modes, but generally we say that the CPUs have two modes. One is the kernel mode, the other one is the user mode. In kernel mode, if your program is running in kernel mode, you can do whatever you want with your computer, okay? You can access everywhere, you can write everywhere, you can read from everywhere. Usually all operating systems are in the kernel mode, okay? If you are in the user mode, okay, you can do only the allowed stuff, okay? You are free to do anything. You are free to do anything about your memory. As long as it is your memory, you can write it, you can read it. Remember, in your C programs, you are allowed to write to anywhere in your memory, but if you do something wrong, your program is going to be messed up, nobody else. So you cannot hurt anybody else if the operating system is behaving correctly, if the hardware is helping right. When you write a C program, it is very difficult to mess up the whole computer. You can mess up your program very easily because you are doing whatever you want with your memory or with your CPU time. Okay? In the kernel mode, if you mess up something, you can mess up the whole computer. That's why the operating systems has to be written very carefully. Okay? That's why even the smallest bug in the operating system running in the kernel mode is a very serious bug. Okay? So we need to minimize those bugs. We talked about that yesterday. Okay, and yesterday we talked about the timers and etc. And we talked about how we do this resource management in time and in space. Some resources, for example, CPU, are multiplexed, shared in time. Some others, they are shared or multiplexed in space. CPU, one example, memory is the other example. Sometimes they are done in both, okay? For example, hard disks, right? I am sharing hard disk both in space and time. Why? Because certain parts of my hard disk is usable by my program. Also, I need some time slot to use that hard disk too, okay? So it is multiplexed in both ways, sometimes dynamically. Okay, so we talked about that too. So wide field of the operating system is the whole operating system. When you say Windows, in the very broad term, when you pay $200 and buy the Windows operating system, that's the wide view. With the Windows operating system, there comes with, even the Paint program comes with the Windows operating system, right? You pay for it. But for us, as the designers or the researchers of the operating systems, we don't consider Microsoft Paint as part of the operating system because we talk about the kernel mode, okay? So that's the unrestricted running of the CPU by the operating system. And we will talk about this definition a little bit even more, okay? So then we came here and we stopped at this point. So any questions regarding yesterday's lecture? Or yesterday I also talked about the how come I have some empty spots here? So can we take more than 50? Should I make it 60? Maybe I should make it 60. How many? 1, 2, 3, 4, 5, 6, 7, 8. Oh, okay, 8, 24, 24, and 24. Well, I think we can take. We have 8 rows, right? Is that correct? So maybe I can take 70 people. Yeah, I'm going to make it 70. Okay, good. So any questions from yesterday's class? Either operating systems or yes?
On Linux, can we write sudo in kernel mode? Or
Say it louder. I can't hear you.
on Ubuntu, if I write
Sudo code.
sudo administrator mode.
Okay, sudo. Yeah.
Am I in kernel mode or is it something different?
Well, no. Well. This one. When you say, okay, that's a good question. This is my kind of Ubuntu emulation. This is not real Ubuntu. This is not real Linux. And it comes back. Yeah, okay. When I say, okay, this command, okay, this ls command, okay, let me show you. So I have 2 things running on my computer, okay, on my things. One is the PS, The other one is the bash. Bash is my shell program. Okay, and these two are running on top of the operating system. Okay, but when you say sudo, okay, it is going to ask me a password for me when I will be running this program ls in the root mode as a user. I am still a user, okay? I am running this program as a user, but as a different user. But I am still in the user space, not in the kernel space, okay? So to be able to in the kernel space, you have to be a operating system program, and no, I mean you cannot interact. Well, you would. There are ways of doing it, but that doesn't make much sense to let the user become a user. Let's say define a user. Whatever that user does can do anything on that computer is not a good idea because users can make mistakes. Okay, so all the programs that I am running through this shell is in the user mode. But I make system calls, right? I make a system call, ask the operating system to delete some files. And those files might be very, very important files. And the operating system will ask me, do you have enough permission to delete those files? And if I am the root, yeah, I have enough permission to delete those files. So at the end, I am not deleting those files. I am asking operating system to delete it. Okay? So you might say that it is the same thing. Well, yeah, but operating system is doing it. I am not doing it. Okay? Well, so that's a good question. Okay, good. So let's go back and let's talk about the history of the operating system. Well, history of the operating system and history of the computer are actually the same thing. They are not that different. Okay? They are exactly the same thing because we are going to go parallel with the generations of the computers. Okay? When the generation of the computer changes, the operating system changes too. So we are going to start with the earliest system computers now, and at the end we are going to talk about our current computer systems, mobile computers, okay, and their operating systems accordingly. So let's start from the 1940s where they invented the. So in 1940s, there were people started realizing that we can do computation, we can do computable stuff with the computers. But in the early days, the computers were very, very primitive. We didn't have the transistors. Okay, transistor is the breakthrough in the computer. That the computer business. Okay, so before the transistors, we had the vacuum tubes. So these are the vacuum tubes. Each one is like a transistor. Okay, now we have billions of transistors on our CPUs nowadays, right? So this one is like maybe how many centimeters? So this is like 3 centimeters, right? 3 centimeters, and this high, maybe 9 centimeters. Each one is a transistor, and we are talking about thousands of them, and each one is power hungry. Okay, they produce lots of heat, and they are very, very fragile. They don't. I mean, usually after running a few hundred hours, they are broken. They need to be replaced. But this is how it's done. That was how the situation of the electronic was. Okay, so that was the computer, the basic building block of the computer in 1940s and beginning of 1950s. Was like that. And ENIAC, you know that, right? You know this. This is one of the famous computers of that era. Okay, it used 17 or 18,000 vacuum tubes, and total power is 150 kilowatts power. Okay, so that's a lot. So that's a lot of power. So that's a lot of heat produced. You have to air condition the room, otherwise your vacuum tubes will go one by one. And if you have 18,000 vacuum tubes, and each one has only 1,000 hours of lifetime, that means what? Every 1,000 hours times this one of them is going to go. So this machine can work can work without breaking down for 1 or 2 hours at most. After 1 or 2 hours, one of the vacuum tubes is going to go. You need to replace them. So they are very difficult to use. And this is how the very, very weak computers, okay? And since they are very, very weak, what's an operating system? It says it's a software, right? To run the software, you need the CPU power, you need the computer power. But these computers are very, very weak. You don't have any memory or CPU time to run anything like an operating system, okay? So they didn't have any operating systems at all. And they didn't have any programming languages at all. So how do you program these computers? This is how you do it. A person basically modifies each bit one by one. 1, 0, 1, 0. Well, this one used the decimal system. It didn't use the binary system. So this person is modifying each decimal digit one by one, like this. Okay? She has the program in her hand. Program is given to her. And she is doing this one by one. If she makes a mistake, then good luck, because it is not that easy to find the mistake in there. You have to go back and check it. So it takes a lot of time to program this computer, and it takes a lot of time to run it too. And since this is a very expensive computer, we are talking about tens of millions of dollars, okay? $30 million computer. So you don't want to keep your $30 million computer idle. This is just a single person. In 1950s, I am paying maybe at most $500 a month for this person, but she is tying up the $30 million computer to program this. Very inefficient, but there is no other way. So there is no operating system. That means that there is no abstraction of the hardware. This is your hardware, and as a programmer, you have to know everything. Okay? There is no abstraction of the hardware. There is no resource management. This is your computer, this is your memory, this is your CPU. You are going to manage it. There is no protection. Okay? If you messed up, I am not going to help you in any way, and that will be it. Okay? So in the first version of the operating systems, there were no operating systems, okay, at all. In fact, there are no compilers. And assembly, well, to be fair, the first assembly is 1952, assembler, okay. You know the assembly language, right? I mean, what is my favorite site? Yeah, this one, Compiler Explorer. Without going to this page, I cannot talk about anything. So this is our MIPS code. So to convert this assembly language to machine code, they didn't have anything until 1950, and it was not accepted that much. So until the second generation of computers and operating systems, they had to do all the programming by hand in machine code, not in assembly code, even in machine code. So no operating systems. The reason is the concept of operating systems were not there. Nobody knew about them. And the computers were really computers. They computed something. What did they need compute? Do you guys remember from the history of the computers? 101. What did it compute? It computed the trajectories of the projectiles, right? The artillery projectiles, top mermilerinin trajektörlerini hesaplıyor. Okay, so you give the parameters. You give the parameters like my cannon is this big, and my target is over there, and this is the wind direction, and that kind of stuff. I don't know exact stuff, but so there is a numerical method. Somebody invented it. So this one is calculating what kind of angle you should use and what kind of parameters you should use while you are firing your weapon. The military application. So it is a very specific machine. So you give parameters, and it computes for maybe an hour, and it gives you a bunch of numbers back. So it just computes. That's why its name is computer. Okay. People did not realize that these computers could be used for other purposes other than the computation of these kind of specific stuff. Okay, this kind of specific stuff. Let's say I have a function. Let's say I have a polynomial. px, okay? Let's say this is a 100-degree polynomial. A, this one, B, this one, okay? So if I try to, this is a one-dimensional function, obviously. If I drive to the graph of it, like that one, okay? And I like to calculate its roots, okay? So I like to calculate, okay? It's difficult to calculate this one. You have to either test it one by one. Is this a root? Is this a root? Is this a root? Is this a root? Or you need to use some kind of a numerical application. We usually use this px minus the derivative of px times some lambda value. So then you need to change this x and take the derivative of p with respect to x and multiply it with lambda and keep doing this all the time. And this is just a single dimensional function. If I have a 100-dimensional function, this becomes more complicated, but the algorithm is there. I know the algorithm. Algorithm is just 5 lines of code, okay? But somebody has to run it over and over and over and again. That's why these are the computers, okay? So we didn't have enough CPU power, we didn't have enough memory, and nobody knew that the computers would be useful other than the computations. When the second generation came, okay, so there are no operating systems, okay. When the second generation came, okay, now we had the transistors, okay, that's the second generation computers. Transistors and batch systems. So they said that, okay, if I am going to spend $20 million on a computer, it better have more than 18,000 transistors. Now we are talking about millions of transistors on a computer. Computers are still expensive, but millions of transistors. That means that, well, thousands of more memory space, thousands of times of memory space, thousands times more powerful CPUs. So what does that mean? And people have realized that maybe we shouldn't code in assembly, maybe we shouldn't code in machine code anymore, maybe we should use an assembly language, right? So they invented the assemblies, and in fact they invented the Fortran language in 1955, I guess, okay? So they have a high-level language, Fortran, which is still being used today, one of the stupid languages of all time, okay? And in a few years they have invented other languages like Lisp, and Lisp and Fortran are kind of, maybe Fortran is the first high-level language, Lisp is the second one. Fortran is the most stupid and Lisp is the most advanced one, even today, okay? So they invented one after the other one. We are still using Lisp today. It's a very, and you are going to learn about it. So they invented compilers. Now, the invention of the compiler is something extraordinary, actually, that changed everything. So I have a program. That program is helping me write my other programs. That's very, very interesting concept, actually. So I don't have to give the machine code instructions for remember this algorithm. I am specifying this algorithm in an abstract language like Fortran or Lisp, and that program is automatically producing the machine code. That was a very interesting idea. So people have realized that we can use the computers to help us use the computers in a better way. So that was the beginning of the operating systems. But the thing is that, again, what am I going to do? I am not going to enter my program like that anymore, because this is too slow, too error prone, and I have a $30 million computer and somebody is tying up the computer now. What am I going to do? I am going to use the punch cards. What's a punch card? Punch card is something like that. Have you seen one of these? You heard about it, right? Have you seen one of these? Just simple cardboard, simple paper, okay? You put holes at specific locations. So that means that I said at the first column I didn't say anything. The second column I marked 1, then 2, then space, then 7. I don't know what these are. I did special stuff maybe. So it's like 1 2 space 7 9 9 6 then 1 maybe. See, I am coding it. So this is just good for the giving numeric data only, but suppose I have 10 digits plus 29 letters, so that would be a punch card too, and that would be a very nice thing. So I give this to a machine. There is a punch card reader. It reads this card. Okay, so I can specify a line. This is a line of code actually. See, what is this? 80. Okay, so 80 columns. You know that most of the terminal widths are 80 columns, right? That comes from these punch cards. Okay, when you open a terminal, usually they are 80 columns or 40 columns. Okay, that's the reason why we have 80 column terminals, because punch cards were 80 columns. Okay, so they invented this. Now I can input my programs and my data to the computers without tying up the computer like this anymore. But it's still slow, because this is something physical. Reading from a physical environment to a computer keeps the computer idle for 95% of the time, because reading from a physical card reader is something slow. So we need to find a solution for that one, but we are using it. The idea of punch cards were not new in 1950s actually. Let me show you this one. People have used, can I do this? Can I make a click on it? Can I touch on it? Anyway, let me open the YouTube myself. Okay, so I am going to show you the punch cards, textile, computers. Yeah, I think this one is a good one. In 1800s, okay, in 1800s, they have invented these punch cards to weave fabric, kumaş dokumak için. They have used it. Let me show you how a weaving machine works. If my computers comes back to life. Okay, so these are really from the 1800, beginning of the 1800. Okay, these are the punch cards for a weaving machine. And let's see, maybe you want to see this.
This is a mechanical Jacquard loom. This technology was developed in France in 1803 by a weaver named Joseph Marie Jacquard. The key thing about this loom is that it controls every warp thread, the threads that go from the front to the back of the loom, individually, because it can...
You see how the weaving works? You have a set of threads, up threads and low threads. Okay, they go like that, and you pass in another thread like this one in between them, right? So if you keep doing this, you get a regular fabric. But if you modify individual threads, those threads is called warp threads. Okay, one by one, then you start getting your nice patterns on your fabric. Okay.
Do that, the loom can create very complex, fancy patterns.
I mean, in 1800, seeing this kind of a fabric was like incredible thing. How can you do that? Because see, you have to modify each of those threads one by one, and as a human maybe you can do that, but you are going to make a mistake after a few minutes. So it just looks like nobody's making a mistake in here, because it takes those patterns from those cards you're going to see.
Patterns in the cloth more quickly and with greater accuracy than the technology available before this loom was developed. These cards are what carry the instructions that are read by the apparatus on the second floor that tells the loom what pattern to create.
Each card is a 80 column thing. So it is obviously it's not 80 column thing, but the number of threads on your fabric, the width of the fabric, and each one is individually programmed. You are saying that, okay, this thread is up, this thread is down, this thread is up, this thread is down, and this is how you are programming it. Obviously there are no loops, obviously there are no if statements, but instructions one after the other one. Okay, so if you have the fixed set of instructions, the length of the instruction doesn't matter, then I can create these kind of nice fabric.
Holes in the cards are read by a series of pins up in the apparatus.
See, these are the pins that read those holes. Okay, if the pins are down, then the thread is down. If the pin is up, then the thread is up. And these pins are reading those holes.
And those holes tell the apparatus which threads down here should be raised for each pass of my shuttle across the warp. Some of you might recognize these cards as looking similar to computer punch.
Well, somebody thought that, I think it was in Germany or maybe in France, I don't know. Why don't we use this as an instruction? I mean, algorithms were there. Algorithm was invented in, I think, 1200s in Damascus, in Sham, by Al-Jabir. So the idea of algorithm is there. Why don't we run our algorithms using these punch cards then? I mean, maybe if we can put this if statements and that kind of stuff. They thought about it, but their machinery was not flexible enough to implement the idea. So they couldn't implement the idea, but the idea of computers were started from this weaving industry actually.
Punch cards. Back in the early days of computer technology, punch cards carried instructions that told the early computers what kind of calculation.
Okay, so the punch cards, 1880s, they were known, and in fact, beginning of the 1900s, they used the punch cards to store business-related information about the clients. For example, the typewriters, dactylo, with the punch cards were common for many businesses beginning of the 1900s with the electrified typewriters, and they were very familiar. So why don't we use card readers to enter the programs? To get the output of the programs, we are going to use the printers. Printers are like typewriters, okay? Punch cards are already up there, but again, printers were slow. Card readers were too slow too. What are we gonna do? They came up with this idea. Okay, they came up with this idea. Idea is this. Okay, I am going to use a cheaper this is a $10 million computer. This computer is cheap. It is only a $200,000 computer. Okay, this is much cheaper than that. I am going to use this computer to read the user programs and data to tape drives, to tapes, and once I have enough programs and data on tape, somebody will take that tape to this expensive computer, and these tapes are much faster than the card readers. This computer will input all those data and program, and there is a system tape. System tape includes the compiler, Fortran compiler, for example, and the libraries. It runs these programs, and it puts the output on another tape. Another person takes these tapes to this cheap computer, other cheap computer, and this computer prints the results. So I keep my expensive computer busy all the time because we have lots of tapes available. I have collected all the tapes from all the users, and I keep loading all these tapes to the computer like that. Okay, and again, tapes are much faster than the card readers and the printers to read the data, to write the data, and that way I can be much more efficient. Okay, the idea is this: if I paid $30 million to this computer, I am not going to keep it idle. This is going to work day and night. Okay, to keep working it day and night, then I am going to, maybe I can sacrifice some time on these 1400 computers, IBM 1400s, but this will be a computer that will be kept busy all the time. It's like the airplanes, right? Airplanes are very expensive. What is the price for this Airbus A380? That's the double-deck airplanes of the Airbus. They are not producing it anymore. I think it is around $500 million. So if you have a $500 million airplane, and airplanes have maybe 30 years of running time, let's say I have 50 years of running time, every year is going to cost me like $10 million. So every day, how much is it? If you divide 10 million to 300, every day it's going to cost me a few $100,000 to keep that plane. So that plane should be up, should be flying all the time. Okay? If I am keeping that plane on the ground, it is only for loading new passengers and loading new cargo maybe, and getting them out of the airplane. That would be it. So that plane should be up all the time, should be flying, no stopping it day and night. It's like the computers like that way too. So that was the computer. So how about the operating systems? I don't see an operating system here. Okay, maybe these persons are kind of operating system, right? So this guy makes a decision which program to read first. This lady makes a decision. Well, they don't make much decision actually. I mean, you just, you put all those programs on the tape, one after the other one. These are batch systems. Batch systems work that way. You read one program, you read the data, you run it, you print your results to this tape. So you did it in a batch way. So let's say I have lots of calculation of the bullet trajectories, okay, for the artillery, etc. So I read all the data, I read the program, I did my calculation in an hour, I printed my results on this tape. I saved my results on the tape. And I read from the tape another program. This say the bank transaction data. I have 10 million bank customers, and I need to calculate their monthly interest values so that I can add those values to that to those. Okay, and I did that, and they took me another 2 hours. But it looks like I am not doing anything regarding the system resource management and the hardware abstraction, right? So I don't have much of an operating system in this case, but there is a system tape. System tape is what? System tape is the system libraries. Maybe I have a few functions that would call stuff like write this data to the desk, for example, to the tape, output tape. As a programmer, I don't have to know about the output tapes. As a programmer, I don't have to know about the input tapes, how they work. I just open a file and write to a file as a Fortran programmer. Well, it looks like we have our operating system forming here. So it is helping us to isolate the input-output related details from the user. So operating system are kind of showing up. Later, they decided that this is inefficient too. So what are we gonna do? Okay, we talked about that one. Okay. So why don't we use this idea of computers are helping us to use the computers in a more efficient way? Okay. So we are going to use those computers to make this idea of efficiently using more computers more viable. So what are we gonna do? Then the third generation computers, okay? these are the real operating systems. And in fact, starting from 1960s, in fact, the idea of operating system comes from 1960s. Most of the things that were invented about computers and the computing systems, they were really invented in 1960s, and we are using still the same ideas. So they invented this multiprogramming. Why don't we keep more than one program at the same time in my memory? What is the advantage of it? Okay, what is the advantage of it? It's like this one. I am going to keep 3 programs in my memory, an operating system 2. If this program needs to write to the disk or needs to write to the tape or maybe send something to the printer, okay, this program cannot continue because for the disk to write something or for the tape to write something, it takes a lot of time. So I'm going to suspend it and I'm going to run this one, okay? And this one is suspended, then I'm going to run this one. This is called multiprogramming, okay? Then who is going to schedule, who is going to run next? That's the operating system. So these are the useful stuff. This is bank transaction job, artillery trajectory transaction job, and this is a numerical job, some other job, I don't know what it is. But I know that none of them can use the computer 100% of the time. They will be blocked. They need some data from the disk, from the user, from somewhere. Okay, they need to do some input-output. Input-output means that they are going to stop, but in that case, the other one will start. Who is going to start it? Operating system is going to start it. That was the idea of multiprogramming. Okay, once you had multiprogramming, okay, once you had multiprogramming, then you don't have to have a cheaper computer like this one or that one, because this program can run this computer can run a program that reads from the card reader and prints to a printer, because they are just simple programs that will be another program running at the same time with the others. If the program that reads from the card reader is blocked, then I am going to run the other programs, right? I am not wasting any CPU time. So this will go away. This will go away. I have a single computer, and I am running many programs at the same time. But it looks that way. There is only one CPU. You can run at most one program at the same time, but it seems like this computer is running many programs at the same time because it is switching very fastly between the programs when it needs to. Okay, so that was the idea of this third generation computers and third generation operating systems. The invention is multiprogramming, keeping more than one program in my memory. If one of them is blocked, if one of them cannot continue, then I'm going to switch the other one. Of course, I need the memory protection between these programs because I don't want any of those programs to mess up the memories of the others, either intentionally or non-intentionally, usually non-intentionally. Okay, so the memory protection with the help of the hardware will make sure that that job can access only its own memory. And hardware will make sure that, that job will not take the CPU forever. Okay, it needs some data, I know. Okay, in that case, it's going to be blocked, and I'm going to let. If it keeps running, then I'm going to stop it by means of an interrupt, timer interrupt. Okay, so that's the memory protection, CPU protection. Once you start storing your programs on disk, okay, it will be even faster to switch between the jobs or loading jobs and then getting rid of the jobs. Okay, so the multiprogramming, spooling is, we are going to talk about it. Time sharing is another idea. Time sharing is like that. Okay, why don't we, if this is my computer, okay, why don't I, these are my terminals. Okay, I have one terminal like that. Okay, and there is a person running on it, and I have, let's say, I have another one, and I have another one, Okay, these are all connected to this computer, my mainframe computer. Okay, each one is running a C shell. Okay, on this computer. So I have C shell 1, C shell 2, and C shell 3. Each one has its own C shell. And I am switching between these three using this multiprogramming idea. So they are time sharing this computer, this CPU, between these three users. These three users, they feel like they have their own computers. Okay? In fact, they are sharing the same computer, but they are sharing time of the CPU. That's called time sharing. So they extended the idea of multiprogramming so that people are running their own programs on this one, but they are interactively communicating with the computer, which is called the time sharing. Okay, that was the idea of time sharing invented in 1960s. Spooling, I am going to talk about it. Okay, in a few minutes. But with all these ideas, we didn't have any of those cheap computers anymore. Okay, and things were much faster, much more efficient. I can support many people at the same time, and that was good all over. Okay, that was good all over. So, but the thing is that there has to be a program named operating system always active in my memory. Okay, this operating system has to use some CPU time, and this operating system has to use system memory, system resources, system memory, disk space, and etc. Okay, and it governs everything. It makes sure that all the programs get their fair share of the CPU and the memory. It makes sure that nobody is violating other people's resources, etc. Okay, so that's the idea of the operating systems that we use today. Third generation computers and third generation operating systems. This operating system, Multics, was very influential. The idea was way ahead of its time. They said that, okay, it is now time. As a power company, I distribute power, electricity to homes, and I bill them every month. So I'm a power company. So I am a utility company, right? I sell power to homes, and I make my money that way. As a water distribution company, I sell water to the homes every month. I measure how much water they used, and as a utility company, I bill them, and they are happy, and I am happy. Okay. As a gas company, I am using the same thing. As a computer company, why shouldn't I do the same thing? I have one large computer at a centralized location. Over the communication lines, I am going to give you guys these terminals, and you are going to share your time on this computer. I am going to bill you every month for your information technology needs. That's the foundation of the cloud computing, right? So it was invented by Multics, and they tried to implement this idea around the Boston area in 1960s. Well, since people were not that ready and the hardware was very primitive on those days compared to today's hardware, it wasn't that successful commercially, but academically it was the foundation of the most of the modern operating systems. Multics is the father of Unix. Okay, so Multics is multiplies the information. I forget about the expansion of it. So they made fun of it. It is not multiplex, it is uniplex. So as you know, Unix is the most widely used operating system, right? This Android operating system is based on Unix. Ubuntu is based on Unix. Mac OS 10 is based on Unix. We are still using the same idea. Okay, we are still using the same idea. And we are going to talk about Multics when we talk about threads and processes. We are going to talk about Unix when we talk about the memory abstraction, virtual memory, input-output file systems, and etc. We are still using the ideas from this Multics operating system through Unix. Okay, it looks like I am out of time for the first part of this lecture. Before taking a break, are there any questions? Yes?
Can we say Multics is starting of personal computers?
Well, no. Multics is a mainframe computer operating system. But with the personal computers, in the early days of personal computers, somebody had an idea. Why don't we run Unix-like operating system on these computers? Yeah, they had the idea. But I mean, the idea of Multics said just the opposite. Not personal computer. They said the centralized computing, our clients are at their homes. That was the idea. Are there any questions from the online people? No? Okay. Okay, let's take a break. Let's be here around 11:37. Arkadaşlar bunu imzalamayan var mı? İmzalamayan.
Hocam dün OBS'in sanırım sesin mikrofonunu açmayı unutmuşsunuz.
Evet ya, bugün açtım ama. Şeyde var ama Teams'de açmışım. Teams'de var. Şeyde yok. YouTube'da yok.
Evet. Listeye en alta yazdın mı? Program olur mu?
Olur. Sen yazmamışsın ki, register olmamışsın ki.
Dün derste katılmadım da hocam.
Efendim?
Dün derste katılmadım da bilmiyordum.
E-mail'lerini oku o zaman.
Tamam.
Tek sen kal. Yok, size basın.
Sen yine kimle dile çekmişsin?
Adam yükseltelim diyor. Ne? Alttan ders alıyor.
Abi benim videolarım yapmazsa hep satın alacağım. Bir şey var. Ne? Ha. Ya yapma. Valla. Saçma sapan şey yapsın ya. Kalbini sen. Tam tersi olur. Dönem bağlı sen. Arada kaldı ha. Öğreteceğim değil mi? Hala. Sonunda bir tane çekiyor.
İşte kredi verir mi? Hiç kredi bilmiyorum.
Ben veriyorum tabii. Kanka bitiyor ama ya.
Okay. So that's the third generation computers. The idea of operating system, as we understand today, were there. It was invented, and one of the many of the classical examples of operating systems started appearing. One of them was Multics, and IBM made a significant progress in those days. Their operating systems and their mainframe computers were very popular. So they were one of the main sources of the inventions in the operating system and the computer area. Okay, so the efficiency is still a problem. Mainframes, those large computers, well, in fact, we didn't have anything other than the mainframes. They still cost millions of dollars, okay? And you cannot afford CPUs wasting idle time, empty time, cycle times. So we need to keep the computers as busy as possible. So those were the motivations for new types of computers, new types of operating systems. Okay, so why are these things happening? Because we now have, I mean, for a $30 million, I can have much more RAM. Okay, I can have much faster CPUs, multiple CPUs, and I can have much more secondary storage. Instead of tapes, I started using disks. Disks are much faster, much more convenient to store programs and data. And since the communication technology is developing to beginnings of the remote access, I don't have to be just in the same room of the computer. I can do the same thing from far away. Okay, so the important concepts of, I mean, along with the developments with the hardware. Okay, remember, the idea of computing something with a machine was there in 1800s, using a weaving machine, right? But the technology to implement those ideas were not available, so that they couldn't do it. And when in fact they get the plans of Babbage, the names of the guy is Babbage. Let me try to find it. You know this from the okay, this guy, he drew up the plans for such a computer analytical engine, and he said that a computer would work like this, but he could not implement his idea because difference engine, because the technology was not that sophisticated to build a reliable machine like that. And I think in 2010 or something like that, they were able to implement his idea using the current technology. Okay, I couldn't find the 2000. Okay, computer pioneer tables. Let me find difference engine. Okay, built from Babbage design. Yeah, this one. So the prototypes weren't that successful. Yeah, I think it was this one, Computer History Museum, 2008. Yeah, okay. So it took people to more than 100 years. Well, they could have done it earlier, but they didn't do it. So the technology wasn't there. So my point is, even if you had the idea of having an operating system, having a compiler, having such and such nice software systems, if you had them, you didn't have enough RAM to hold your program and the operating system at the same time. Even if you had it, your CPUs are not powerful enough to support all of them. Okay, so in 1960s, with the help of the integrated circuits, you put more transistors on a single chip. Okay, then the idea is kind of became feasible. Now I can have the operating system. Now operating systems can help me to isolate the details of the underlying hardware. Now operating system can help me manage my resources. Okay, so that was it. So multiprogramming idea in 1960s again, third generation operating systems and computers, running several programs at once, Well, the idea, you know what we mean, right? On a single CPU, you run a single program at the same time. That's it. It could be either job number one, job number two, or your operating system. You cannot run your operating system and your program at the same time. It is either one of them or the other. Okay? But seemingly, as we humans, it looks like they are running at the same time because the switching is so fast. Okay? Because the switching is so fast. So when you hear this, when you see sentences like this, running several programs at once, take it that way, because our book and our lectures, our discourse, will assume that we have only single CPU in our systems. Okay? Extension to multiple CPUs is possible, but we are going to assume that we have a single CPU all the time. So when you say several programs at once, there is a there is a multiprogramming happening. Okay? So if you're running multiple programs at once, then there has to be protection against the others, either intentional or unintentional access violations. Okay? And when you are doing the multiprogramming, when one program needs to do I/O input output, okay, I am waiting for my input from the keyboard. Well, users are slow. They are millions of times slower than the computers, right? So what am I going to do? I am going to wait until the user is ready. That's wasting the CPU time. No. So what am I going to do? When I need the I/O, when I need the input from the user, I am going to be blocked. Okay, my process, my job will stop, and some other process will use the CPU. That's the idea of the multi-programming. Okay, that's the idea of the multi-programming. When one program needs to do I/O, let another program use the CPU. And there is this important idea of preemption. Preemption is this. If a program took the CPU and it is using and it doesn't need any input-output needs, it is not expecting for any input. Okay, it is not expecting any input. It is not doing any output. It just keeps using the CPU, doing some mathematical computation. So what do the other programs do? They have to wait. This kind of situation is called starvation. Starvation is like the starvation that you know, kıtlık, açlık, whatever you call it. Okay, they are starving for the CPU, but they can't get the CPU because somebody took the CPU and it is not giving it to me. Okay, well, in that case, that process has to be preempted. It has to be stopped, and it has to be blocked. And by stopped, I don't mean that it has to be aborted. Okay, it has to be suspended so that it can continue later when the other processes get their fair share of the CPU time. That's called the preemption. And as we talked yesterday, preemption is done with the help of the hardware, with the help of the timer interrupts. What did we say? From the earliest days of from 60s, we have this timer interrupts. Timer interrupts happen maybe 50 times a second. Okay, and those interrupts are handled by the operating system. When a program is running, okay, timer interrupt happens. Operating system takes that interrupt, handles it, and lets one of the processes take the CPU. So it could be the same process or some other process. So if I am going to stop a process like that, it is through the preemption. So nobody can take the CPU and take it forever. Okay, it's not you are not allowed to do that. Okay, same idea with the daemons. Daemons are okay, spooling, simultaneous peripheral output online. There is a daemon. There is a, let's say, this is our memory. Job number 1, job number 2, job number 3. There is this daemon, spooler daemon, and we have our operating system. The responsibility of daemon is this. It looks for input from the punch card or from some other place, and it looks for output to the printers. If, as a job 1, if I need to send some file to a printer, I send it to this daemon, say that, okay, print this file for me. And job 2 does the same thing, and job 3 does the same thing. This daemon, okay, always waits. It is always blocked. It waits for file to print. If there is a file available to print, then it starts sending the characters one by one to the printer. Since printing takes time, once it sends a character to the printer, after that it blocks for a while. And when the printer is ready, it sends an interrupt saying that I am ready. Then operating system handles it, and the daemon sends another character. So daemon is just like a regular job, regular process doing the printing for me. But as a job, I think that my file is printed as soon as I send it to the daemon. Okay? So daemons are like that. And the spooling uses this daemon idea, multiprogramming idea. So that means what? Without multiprogramming, spooling wouldn't work, right? For the spooling, you need multiprogramming, okay? Without the multiprogramming, since spooling wouldn't work, without the multiprogramming, then you have to have one of those cheap computers to enter the data, cheap computers to output the data. Otherwise, your main computer would be inefficiently used, okay? So multiprogramming was a very good idea. It was very, very useful in terms of keeping our expensive computers always busy. Okay, we talked about already this. You are going to see this picture a lot. Okay, many jobs, user jobs, and operating system, and in my previous picture, and I put a daemon job in there too. And most of the stuff that I showed you yesterday on my computer, okay, Windows Task Manager. So these are my tasks running. Okay, most of them are blocked, as you see. They are using 0% of the CPU. They are waiting for something to happen. Okay, they are all blocked, and they are not supposed to take any they are not supposed to take any significant amount of memory. See, it just takes 1.3 megabytes of my memory, but they are just waiting. They are not doing anything. This bash is not doing anything. Okay, most of them I don't know what they do. Maybe if I go into the details of it, I can see it. Okay, I don't know what it does. Windows related stuff, operating system related stuff. Some of them run in the kernel mode. Some of them don't run in the kernel mode, but they are all there. Okay. And most of my CPU is used by who? Is used by this recording software, and then this team stuff. And most of my memory is used by Teams, and then this OBS stuff, then the Chrome, okay, and this board stuff. So operating system doesn't keep this kind of table for me to learn about my processes. It uses this idea for what? Why does the operating system need this kind of detailed information about the processes? Can anybody tell me? Why do we have such sophisticated statistics about each process running on this computer? I'm going to tell you, it is not for just showing me. Okay? Yes? Say it louder.
To make the memory areas distinct.
To make the memory what?
Distinct. Different.
Well, without knowing how much memory they are using, how is it going to make the resource management, right? That's one thing. The same thing for the CPU. When I schedule processes, let's say a timer interrupt happened. As an operating system, I handled it. Now I have to make a decision which process is going to use the CPU time. Okay? If Teams says that I am ready to run, if OBS says that I am ready to run, if Google says that I am ready to run, I need to choose one of them, right? I need to look at these statistics. Who has used the CPU most? Then I'm going to let the other ones use the CPU now. If somebody says that, for example, this one, I don't need the CPU, then of course I am not going to wake it up. Okay, it will keep sleeping. Okay, so this kind of detailed statistics is always available, for the operating system. And of course, it takes time, it requires memory, it takes CPU time to keep all those statistics. Okay? It is the task of the operating system to keep all those statistics, and it will use those statistics to make a scheduling decisions, to make memory resource management decisions, and other kind of stuff. Okay, that's why it needs lots of memory operating systems. Okay, good. then there are fourth generation computers from 1980s. Transistors got smaller. Okay, when the transistors got smaller, that means what? I mean, instead of building very large mainframes for $10 million, $20 million, I can have the same power PC for $2,000, and I'm going to call it a personal computer. In 1980s, with the invention of the large-scale integration like the Intel chips, 4004, 8008, and 8086, okay? These kind of small computers became available, and if there is a computer, then you need to manage the resources. There has to be files. How am I going to open the files and read the files? As a programmer, I need an operating system. So for the IBM PC, IBM has selected this Bill Gates DOS operating system, the disk operating system. So actually, Microsoft did not write this operating system. They bought it from somebody else. They called it Microsoft DOS, okay, and IBM made it its official operating system for the personal computers, and we started seeing these kind of operating systems for the small computers, okay. So the idea of the graphical user interfaces were there even from the beginning, from 1960s, okay. Even people started using the keyboards or the screens. The graphical user interfaces were there using the oscilloscope interfaces. Using the light pens and the oscilloscope interfaces, the ideas were there. And in 1960s, this guy Engelbart, just look him up in YouTube. Okay, you are going to see his demos from 1960s. He's using the name mouse. He defined it. He doesn't know why he called it mouse. And he says he's sorry about the mice, the real mice, okay. And he talked about the Windows icons and menus and etc. When Steve Jobs saw those kind of demos in 1980s in some place, he decided that his personal computer should have an operating system like that. Then he insisted on that idea. And you know the rest of the story actually. This Apple company in 1999 said that, okay, I'm going to give up developing my own operating system. I'm going to base it on this BSD Unix. As you know, Unix is a simplification of the idea of Multics. Okay, so the whole Apple world switched to the Unix. And this Windows NT and later the Windows versions, they all are affected from the ideas of 1960s. So this is the fourth generation personal computers. The motivation for the personal computer operating systems were different. Efficiency is important, of course, but my motivation to use this computer is not for efficiency. Okay, I am using it for writing emails, okay, writing papers, reading papers, doing the presentation, doing that kind of maybe a little bit computation for this one. I don't keep this computer up day and night, okay, because this is not a very expensive computer, only $1,000, okay, and efficiency is important, but more important is the interactivity. My time is more important than this computer's time. So when I click on something, I immediately expect it to respond to me. Otherwise, I am not productive, right? So efficiency went away. The concern of efficiency went away from the personal computers. The important thing became the interactivity. So how does the operating system work to make it more interactive? So the graphical interface is going to help. Okay. Other kind of ideas are going to help. Still, the multi-programming is going to be, and time shading is going to be a lot helpful in this case, and we are using multi-programming in our modern day personal computer operating systems. Okay, so the efficiency is not the first priority. Of course, they are selling servers and mainframe computers. They are still selling them. Their number one priority is their efficiency. Okay, when you pay $200,000 to a computer for your servers, you don't want to keep that server shut down. That server should be up and should be serving your customers for your company, right? Because you paid lots of money to that. But I am not saying the same thing for this computer. I am not saying that I should keep this computer running all the time. Okay, then another revolution is the 5th generation computers. Those are the mobile computers. When things got even more smaller, okay, even smaller, much more smaller, then we started having personal digital assistants. Very small handheld computer. It is keeping lots of your personal data, your contact information, your calendar, and etc. Then this Ericsson people in 1997, they came up with this idea of smartphone. Why don't we combine the personal computer with a phone, and we are going to call it a smartphone, and that would sell a lot. They were right, okay, they were correct that this would be a good idea, but they were not correct that they would make much money on it. Some other people will. Usually that's the case. If you are a computer scientist, if you invented something, usually you are not going to make much money on it. Somebody else is going to make money if the idea is good. Because the times are, sometimes times are, what did I say? They invented this graphical user interfaces, touch screens in 1960s. Okay? PDAs were available in 1980s. Many companies tried it. Only a few companies made lots of money using these technologies. So making money and invention are two different things. Usually the smart people, they don't make money. Only other type of people, they make money. Okay. So as far as I know, Ericsson is gone. Their invention still stays here, and people are making lots of money. So the BlackBerry, they were one of the companies to make good money on that one, but later they missed the touchscreen revolution. Apple made lots of money because it used both smartphone idea, touch screens, and interactivity, and etc. And later came Google. Now Linux-based Android operating system, which is Unix-based. Okay, I think it is the most commonly used operating system of all time. And the main concern for this mobile computer operating system is battery management most of the time. Okay, security and battery management. For a mainframe, power management, well, it is important. Maybe it is the 5th important, 10th important thing, but it is not the first thing. For a mobile computer, battery management, interactivity, security, these are the top motivations for your operating system. You have a very interactive, very nice operating system, but it is using up all of your CPU time. It is using up all of your battery in 2 hours. Then it's not useful for me. It's not going to do anything. So for the PCs, interactivity; for the mobile computers, interactivity, battery management, and security. Okay, these are the nowadays important things. So basically, if I go back to this slide that talks about generation of computers and operating systems. Okay, in this book and in this course, basically we will be mostly talking about this era. Okay, multiprogramming, okay, time sharing, virtualization, memory abstraction, input output. Most of the ideas that we are going to talk about will be coming from this era. Okay, when it comes to interactivity, security, communication, Well, those are different chapters at the end of the book. I don't think that I will have time on to talk about them. We have advanced level courses at our graduate program for the graduate level students. We talk about them there, but in this case, in our course, we will not talk much about them. Maybe about virtualization a little bit, but not much. Okay, so main ideas we will talk about these. Good. Any questions about this history of the operating system / the computers? As I said before, this is not just the history of the operating system, it is also the history of the computer hardware too. The idea happens like that actually. We had the mainframes, they are very, very expensive, okay? They have to solve some problems like the protection and etc., etc., etc. Once you solve all those problems, the hardware becomes even smaller. Then you have your mini computers now. You solve the same problems for the mini computers. Then the hardware got smaller. Now you have your PCs. You solve the same problem with the PCs. Then your hardware got smaller. You have the mobile computers. You solve it for your mobile computers. So it looks like we keep solving the same problems over and over again for different platforms. Nowadays we have credit card computers. You know the credit card computers? Your smart credit cards, they are computers actually. They have a computer you have a computer in those credit cards. Whenever you put them in the credit card slot, okay, that computer boots up. There is an operating system in it. It has its own task. It performs it and it shuts down. So it's a very primitive computer. It has an operating system too. And you need to solve problems for that kind of environment. So we keep solving the same problem for different kind of environments, and we are going to talk about it. That's why looking at the history is important, because you need to recognize the problems, and you need to recognize that you have those kind of problems for your new type of computers available for today. Okay? So looking at history and looking at the operating system ideas from the history, that's why it is important. Okay? We don't study history just for the fun of it. Okay, it is fun really, yeah. What the people think about it, but it is important to understand why we are using Linux nowadays. Okay, why is it so popular? Okay, where did the idea come from? So history most of the time defines many of the things why we are doing the current things today. Now I'm going to look at the computer hardware. We are going to make a little bit review of it. Well, this is not a hardware course. This is operating systems, but operating systems run on top of the hardware, and they need to know detailed hardware information. That's why we need to talk about the hardware. I mean, operating system's job is to isolate the hardware details from the programmers. But as an operating system, I need to know about the hardware so that I can isolate it. So we will be talking about the hardware a lot, and this is just a small introduction to the computer hardware. Okay. At the center, we have our CPU. Okay, our most important resource on a computer. Okay, along with the memory, CPU and the memory. What is MMU? Does anybody know what MMU stands for? Memory Management Unit. Yeah, Memory Management Unit, MMU. So why MMU sits? What is this? What is this gray line? It is called bus. Bus is your communication line between your CPU, memory, and the other computer elements, like your controllers and etc. Okay, so if I like to communicate with memory, I need to go through the bus. If I like to communicate with your video controller to send something to the monitor or the printer, I need to communicate through the bus, system bus. That's why I know. But can anybody tell me why this MMU is here, Memory Management Unit? Why it is not here, but there? It is inside the CPU. Virtualization, memory virtualization. That's the key. Okay, let me talk about the MMU. The task of the MMU, okay, it's a hardware component obviously. Okay, if I am a process, let's say I'm P1, when I run my instructions, when I try to reach some part of my program, okay, I say that, okay, put this number 012 to this address 0152. Okay, if P2 says, well, I am going to put 55 to 0152. Okay, what is going on? Are they trying to write to the same location? Well, the answer is no, because P1 and P2 have different spaces in the memory. Okay, but they think that they have the whole memory for themselves. That's the memory virtualization. So it is the task of this MMU to take this address and change it so that this part of the memory belongs to P1 and this part of the memory belongs to P2. So P2 is using this part of the memory using this address, but P2 is using this part of the memory using this address. They think that they have their own memory space. Well, in fact, they have, but it is the MMU that does this address translation for these process 1 and process 2. Okay? Since MMU knows which process is running, okay, MMU should know about it. Well, okay, this is P1 is trying to access this one, so I am going to give this part. This is P2 trying to access this one, so I am going to give you this part. So MMU is a very central part of this memory virtualization, and it's part of the CPU actually, and you program it. You tell the MMU that, okay, this process 1 is going to use this part of the memory, and this process 2 is going to use this part of the memory. Only operating system can change the parameters of the MMU. If you like to change something about the MMU, if you like to program it, you have to be in the kernel mode. Okay? You have to be in the kernel mode, and only operating system can be in the kernel mode. As a regular program, you cannot touch MMU. Okay? MMU is very important, and chapter number 3 is all about the memory virtualization and MMU. And we will talk about it. We will talk about its structure, and we will talk about how we use it. And in fact, in your homework number 3, maybe, you are going to implement a simple MMU program. Okay? So MMU is important. So CPU sits on top of the MMU and the system bus. Okay? Memory is like that. You can communicate with the memory saying that I am going to put this number into this location, or I am going to get the number at this location. That's what you can do. And also, as a CPU, you can communicate with this controller. This controller has registers in it, like that, small registers. Okay, when you put a number in it, let's say I put a number 10 or 65 in there. Okay, 65 is the ASCII code of the letter A. You're going to see an A at this position. Okay, that's the job of the video controller. It has some special memory in it, special registers. As a CPU, I can modify them. Once I modify them, this character just shows up there. So I am just programming this video controller, right? That's what I am doing. That's how you do the output. So how should I know which address is this? As a regular programmer, you don't know about it, because that part is the responsibility of the operating system. You are not allowed to directly write to these locations as a regular program. Okay, only the operating system in the protected mode, kernel mode, can do that. How about the keyboard? Keyboard has a special register like here. Whatever you read from this position, it is the code of the button that the user presses. Okay, if the user presses this button, then the code of that button is written here, and you read that value from the CPU using a special instruction. And again, as a regular programmer, you are not allowed to read this address directly. You can ask the operating system to return you the next character, but you cannot go into the keyboard's controller and read stuff. Okay? So if I had the whole computer myself as an operating system, I can do whatever I want. I can access any part of the memory. I can access any part of this controller or the keyboard or the USB controller. But as a regular programmer, life would be very, very difficult for me. I mean, without getting any help from the operating system. If there are no operating systems, then I have to know about all of this detail. Okay? I need to know about the details of the MMU and the memory, video controller, keyboard controller, hard disk controller, USB controller, etc. But luckily, I have the operating system. I don't have to know anything about them. All I say that just scanf, get some number from the keyboard, printf, print something to the monitor. Okay, so that's the idea of hardware abstraction for me as a regular programmer. Okay, good. Are there anything that I'm forgetting about this picture? We will talk about this is a very, very overly simplified picture, by the way, because nowadays we don't have a single bus, right? We have very specialized bus types for our modern day computers. What is the most specialized, most important bus for modern day computers? Other than the system bus, there is a very fast, very important bus for our what?
GPU bus.
Yeah, the video controller. So there is a direct line between CPU, memory, and the video controller. Okay, so GPU is actually a video controller, graphics processing unit. So most of the time these controllers are electronic devices, obviously. Most of the time these are computers. For example, this hard disk controller is a computer by itself. It has its own operating system. That hardware is so complicated. To drive this hard disk drive, you need a sophisticated computer here in the controller, right? So your CPU communicates with that controller. Okay, for the video controller, GPUs are very sophisticated, and since they need lots of data very, very fast, this bus becomes so slow because I need to share this bus along with all the other peripherals. So what am I going to do? I have my own special dedicated video bus. So I am ignoring those kind of details, but this is good enough for me to talk about the hardware on our personal computer. Again, I'm not going to teach about the details of the hardware, but without talking the hardware, you cannot isolate the hardware. That's what the operating system does. Okay, you are so quiet. Nobody's asking any questions. Okay, let me get one or two questions, either from the online audience. Are you alive? 7 plus 74 people. Are there any questions?
No, sir.
Somebody said no. Okay. He liked it. Are there any questions? I need questions, okay? I'm going to stop as soon as somebody asks a question, otherwise I won't. Yeah.
What's the difference between kernel and operating system?
Well, you are asking me this question. Kernel is the part, okay. Remember that one? The wide view of the operating system and the narrow view of the operating system. Okay. When you pay $200 to Microsoft and buy the operating system, Windows operating system, the whole thing that you buy, the whole box, the whole software, is the wide view of the whole operating system. That includes the Windows operating system, the Paint program, the Notepad, the calendar utility, and etc. Right? They all come with the operating system. But not all of that software runs in the kernel mode, because kernel mode is the mode where CPU can do whatever it wants. Okay? Kernel part of the operating system runs in the protected mode, kernel mode. Okay? So that's the narrow definition of the operating systems, and that's what we mean by operating system. Okay? So most of the stuff, when I see this, most of the stuff that I am showing you here are part of the Windows, right? Are part of the Windows, most of them, but most of them are not running in the kernel mode. They are like regular user programs. They cannot do whatever they want. Okay, they are restricted. Why does the Microsoft restrict itself? Why they are not running these in the kernel mode? Because kernel mode, well, it is useful something, but it is so dangerous to run. Why? Because if by mistake it does something, if by mistake it modifies a very bad memory location, then it's going to crash the whole computer. Maybe I'm going to lose lots of data. Maybe it's going to damage my SSD disk, right? So I don't want to do that. So you don't run any programs, any part of your operating system in kernel mode unless it is necessary. Okay? Most of the file systems, they run in the user mode. If they need to do something, it asks the operating system to do it for them. We'll talk about, there are some operating systems with a very small kernel. They say that if I keep the kernel small, then there is less possibility of having a bug in the kernel mode. So that's a good thing. That's a good thing. Okay, that's a good question. Any other questions? Good. So there are 50 people here, and my attendance sheet is, so it looks like I can have maybe 15 more people. So I am going to increase this number from 50 to 65, maybe even 70, because some of them will not come. Yeah, I am going to make it 70. Okay, I will see you on Monday. Thank you. Efendim?
İmza atamadım ben de.
İlk ders aldım ve ilk ders geri attım öyle. Yani ders arasında da sordum. Sen yeni mi geldin?
Hocam biraz geç geldim ben de.
Tamam, gelecek sefer erken gel.
Bir şey sorabilir miyim?
Zor değilse sor.
Sorayım. Şu anda mesela şey dedik ya, sadece single core'lar için bu dersi
Bir tane CPU'muz var diye düşündük, evet.
Mesela şu anda hani çoğu bilgisayarda özellikle işte yani çoğu bilgisayarda
Çoğu bilgisayar değil, satılan CPU'ların hepsi
multi-core.
evet.
Hatta bu M1'la falan multi-core'un da artık daha da
Evet, onda suyunu çıkardılar.